I guess 8 deals with projectile motion, and then 9 is escape speed. Probably should have moved question 9 earlier, be with its like kind. All right, any questions with this? I'm going to start talking about chapter 9 stuff now. We've covered them. Why I'm having such difficulty this semester with 2 classes. Too similar in terms of topics. So if I'm near the surface of a planet, if I know what the acceleration due to gravity is, I can find my weight, just take my mass, multiply times whatever g is. I could also, even if I'm out in outer space, I can still find my weight at that point. In other words, the gravitational pull, if I know what the value of little g is. The trouble is, it gets a lot more difficult once you get to outer space, or if you're dealing with really small objects. So there's a generalized formula for the gravitational force. I feel like I've written this on the board when I talked about potential energy, but there was a, I think a Okay, I got at least one nod. It does depend upon, well, gravitational forces. We flash back to when we first started talking about forces and what are the requirements. Gravitational force requires 2 masses. So those 2 masses have to come into play. The greater the mass, the greater the pull. Depends on how close they are, so r squared. And then depends upon this gravitational constant. So right there on the board, we have 4 things that students all want to call gravity, and this is why I get really picky about that. This is weight, or force due to gravity, acceleration due to gravity, force due to gravity, gravitational constant. Gravitational constant depends upon what unit system you're dealing with. 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Did I do an example before of what the actual force is between 2 objects using this formula? Okay, so let's do it. My mass is about 91 kilograms right now. That's my mass. Mass G. G for George, not gravity. The mass of the textbook right there, half kilogram. So mass of book, we'll say it's 0.5 kilograms. Right now that book is about 1.5 meters away from me. So the distance between us is 1.5 meters. So there's some gravitational pull with 2 masses, so there's a gravitational pull there, and we just, at this point, it's a plug and chug exercise. Now, if you do not have your calculator here today, please, at some point, make sure you know how to use your calculator to get whatever answer we end up getting. There are a number of students in the past that have had difficulty being able to figure out how to do exponents with this. They often throw in an extra factor of 10. But the way you would do it, that force due to gravity between that book and myself is 6.67 times 10 to the negative 11th times my mass times the mass of the book divided by that distance squared. And if someone would be kind enough to actually do the calculation.
So are we leaving G just like it is, and then
Yep, G is a constant, so.
Okay, so it would be G 45.5 over 2.25. So we divide, okay, I see what we need to do.
Yep.
I'm probably wrong, but 1.3488 negative 9?
Times down to the negative 9.
Times 10 to the negative 9, sorry. Do you want all the 2's at the end of it, or no? Do you want all the 2's at the end of it, or no?
No.
Okay.
That's fine in terms of if that's the actual number. We need, did you say twos or units?
Yeah, there's,
A bunch of twos?
5 2's at the end.
Yeah, okay, I'm not worried about the
Okay.
twos. What are the units, by the way?
Newton meters squared over kilogram per square.
That would be just this part,
Alright.
but 2 kilograms here, this is meters. Let's do it the old fashioned way. So we have Newton meter squared per kilogram squared times kilogram over meter squared.
Kilogram.
To me, the simpler approach is to ask myself, what did we actually just find? What was the quantity we found? How to get that? That's what someone told me.
Is it just newtons?
What'd you get? Okay, this is gonna be a lot closer. I'm feeling pretty, I feel like this is about right. This seems right to me. I know the answer's not negative. There's no negative numbers in here other than the exponent. All right, so on the calculator, when you type it in, I think on most of your calculators, there should be a button that either has an E or an EE button. So you'd hit 6.67 EE or E negative 11. This E right here represents the times 10 to the. Oh, you're using your phone? Okay. I don't know. If you're using a TI-80, whatever, I think they have an EE button.
Now, I didn't use the E button because I don't know how to do that.
Okay,
But
you
I
used
used
the-
the exponent.
You did times 10 raised to the negative 11?
Yeah.
Yeah, and that's the same thing. The E or EE button is just basically substituting that bit. Because when you gave your answer, and you said 1.3488 negative 9, was there a letter in there? Like
Yeah, it was the E, it's the 10 to the negative
Yeah.
9. Yeah.
All right. Do we actually get two people who get the same answer?
Yeah.
Okay, we did, okay. So if, at some point, please make sure that you can use your calculator to get this answer. But we still haven't quite figured out what the units are. So, Lacey?
I had a question about that. Whenever we're writing it, can we just put the E or do we have to put times 10?
At this point, I've accepted the E as legitimate notation, so 1.3488 E negative 9 I would accept.
Okay.
But I would still take off 3 points on a 10-point problem if you left that as your answer, because we have to resolve the units.
Would it be newtons over kilograms to the third?
No.
Would it just be newtons?
It would just be newtons. We found a force, newtons. Now, in terms of how do we get newtons out of this whole mess here? Well, I have kilograms squared here, times, that's in the denominator of that, looking at that, times kilograms, so I got kilograms squared here, so those two would cancel out with those two. Now I have meter squared over meter squared, which cancel out, and and I'm left with just meters, or, sorry. newtons. All right, let's do one other plug and chug here. Let's figure out what my weight is using this formula instead of this formula. Actually, let's do them both. Let's see how close we get. All right, so my mass is about 91 kilograms. Winston-Salem, G is 9.798 meters per second squared. So using the classic W equals mg, not W equals milligrams, as some text readers will tell you. What do we get as my weight?
$891.
891
Point six
618.
units?
Newton.
Yeah, I noticed that on the test, in 110 students, it's not atypical. When asked for weight, some students really love to put it into pounds. Not necessary, not wrong, it's just not necessary. It's extra work you don't have to do. All right, so now let's use this formula here and see how close we get. So 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Times my mass, 91 kilograms. Times the mass of the Earth, 5.98 times 10 to the 24th kilograms. Divided by R. What is R? So, okay, what would what radius am I using?
Where does the limit
It would be the distance between me and
the
the,
center of the Earth?
is it the center of the Earth or the surface of the Earth?
Center.
Should have stuck with guns. Try again. Center of the Earth or surface of the Earth?
Center.
Like you mean it.
Center.
There we go. Yeah, it's center to center distance. If it were not, if it were actually to the surface of the Earth, think about it. You go out, you touch the ground with your hand, R becomes incredibly tiny. Square it, becomes even smaller, and suddenly that force is huge. You would never get your hand off the planet. It is center to center. All right, so in essence, radius of the Earth. 6.3, I want to say 6.38. What does Hewitt do? He does 6.37. 6.37 times 10 to the negative, not negative, times 10 to the 6th meters squared. So roughly 6.4 megameters is the radius of the Earth. If your answer is not somewhere around 891, I mean, it could be a little bit off, but if you're not in that ballpark, then you've done something wrong. So, the question,
Yeah.
Isabella?
When did you put 5.98 times 10 to the 24th?
This is the gravitational pull between me and the Earth, in essence, my weight. So that is the mass of the Earth. If you're ever not quite sure, you can always just go into Google. Sorry, Tana. You can go into Google and just type in mass of Earth or something like that. But almost every physics textbook is going to have that information either on the back, inside of the back cover, or inside the front cover. 894.5 units.
Gosh, are you?
Yes. All right, so I'm off by, these two different methods are off by 3 newtons out of almost 900. Because I just happen to know this value here, I'm feeling comfortable that this is more accurate. But I hope you can see that they are close enough. This is probably the one, this number right here, probably we would need to make more specific to Winston-Salem to get them to match. We're done at 220. Okay. Yes, Isabel?
Just one more question. Whenever we were working on the energy equations, this equation was different. It was negative, there's a negative G plus a constant at the end.
Oh, that was for potential energy.
Okay.
Not the potential energy has a negative in front and then plus a constant afterwards. Force is, this is the force one, where it's squared. Potential energy just has an R on the bottom.
Okay, sure.
Okay.
It's supposed to be different.
And I will say that in 251 and 151, where we go into more detail on this, at some point, my potential energy formula, I'll square the bottom just out of habit, because I write this one so much. Is there another question? All right, let's take a break, stretch legs, then we'll talk about our sun becoming a black hole, or not, and potentially the destruction of all that you know. Not the same way we'll do if we ever discuss second law of thermodynamics, then we really will talk about the destruction of not only everything you know, but everything. But in the shortened course, I tend to skip over that. Yes? Okay. Let me see what you're typing in. Okay. All right, that's the numerator.
That's what I wanted to on mine, like, I can't
All
figure
right.
out how to make it work.
It's if you count over, basically, that should be 9 places, 1, 2, 3, yeah. So that's 1 times 10 to the 9th. You want scientific notation. It's gotta be in there somewhere.
So try and do it in this one, and see if you get that. Okay.
They on the inside cover there. Ah. Calculators I had
Yeah.
20 years ago had it, so that's gotta have it.
Cause I did the EE thing, like he was saying.
Yeah, and it comes up.
See, normally it's just calculators automatically and something like that would build into it, but that's just better
I
something
didn't
that
get
doesn't cost.
calculators, I went through this, yeah, I found this one was. I went through the pre-calculus algebra with just this, and I downloaded it, really needed that, cause it was.
It's not saying.
You should have put them on
Here.
like, I had one, I was just using.
None of those. It's not that, not that. It's that. That's statistics stuff.
So it's just because of notation.
Yeah, oh, there we go. It's that button, that FE button, that's between, I think, fixed and engineering. Or, yeah, engineering, so 1.3488 into the negative, that's the negative 9.
Thank you.
Now-
And it's processing information, I'm guessing they're transferring.
Yeah, you don't have that,
To where they're gonna send it.
oh, SCI,
Yeah, that is very.
that was inside this communication. And to get out of that, okay. So FLO takes you out, SCI puts you in. E and G is similar to scientific notation, except E and G make sure that it's always 10 raised to the some power of 3.
Okay.
And that's fine, there's nothing wrong with it, it just for some reason engineering notation.
So
Typically-
once I get my answer, I would do second and then this.
Yeah,
Okay.
that should do it.
Okay, thank you.
So, I guess F is, as I said, fixed, I think it's floating for an engineer.
And so
Yeah.
I don't know. This one.
I got this one.
Something is still
Come on.